So for those of you who aren't following the notes along, Sergey is going to talk about data-driven, high-dimensional design for trustworthy drug discovery. Sergey, just a quick bio, is assistant professor of electrical engineering and computer science at UC Berkeley, and his work focuses on machine learning for decision-making and control with an emphasis on deep learning and reinforcement learning algorithms. Applications of his work include autonomous robots and vehicles, as well as computer vision and graphics. His research includes developing algorithms for end-to-end training of deep neural network policies that combine perception and control, scalable algorithms for inverse reinforcement learning and deep reinforcement learning algorithms. So I'm really pleased as a fellow UC Berkeley person to introduce Sergey to present his research this morning. Thanks, Sergey.
Thank you for the introduction. So this is a joint project with my colleague, Professor Jennifer Listgarten. I'm going to primarily talk about work from my lab today, just so that I can zoom in on one particular project, but this is kind of part of a line of work that both Jennifer and I are collaborating on. And some of you, and Jennifer Listgarten, for those of you that don't know, she's an expert on machine learning for computational biology applications. So some of you might be wondering at this point, well, okay, if my bio is to be believed, it seems like I work on robots and graphics and things like that. So what the heck does that have to do with drug discovery? A lot of my work is on reinforcement learning algorithms, which are algorithms for computational decision making. And really the concept behind this project is to combine state-of-the-art ideas for algorithms for decision making with state-of-the-art models for computational biology applications, with the idea being that we can then use these models to make decisions in a robust and reliable way. So let me kind of explain some of the issues, and then maybe it'll be more clear why we actually need to take decision-making algorithms seriously in this context. So one of the things that I think most of us can agree on is that current predictive models are really powerful. So if you want to train a model that will predict, given a protein sequence, how well will that protein catalyze some reaction, or given a chest X-ray, what's the probability of that patient having a particular disease, right? These are things that you know, there has been quite a bit of work on. There are results that look pretty compelling, and it's very tempting to think that if we can predict properties of interest for molecules, proteins, what have you, perhaps we can then use those models to design better drugs, better enzymes, better, you know, whatever you want. And there's good reason to believe that might be true, because current algorithms for automated decision-making are also been demonstrated to be very powerful, albeit in somewhat different domains. So for example, reinforcement learning algorithms, where you have agents that learn through interaction with their environment, have been demonstrated to work effectively for things like playing video games, controlling robots, both in simulation and the real world, and even beating the world champion at the game of Go. So we could ask, well, what if we put them together and we automate the process of decision-making for things like, synthesis of new molecules, drug design, medical treatment plans, things like that. So can we use this kind of reinforcement learning process to train up models that perform these real-world impactful tasks? What could possibly go wrong with this? Well, it turns out the problem is not nearly that simple. It turns out that there's a major kind of statistical mathematical problem that comes up when you start using these powerful models that I mentioned before, that have been proposed for predicting properties of molecules, properties of proteins, and so on, when you try using them for designing new drugs, new molecules. So just so that we're on the same page, kind of a very high level outline of what it looks like to use a predictive model for design. Let's say that you'd like to design a protein, for instance, right? So you might collect some data from all sorts of experiments that you've done. So maybe you've synthesized 1,000 different proteins, you conduct some assay on them, and you measure some property that you care about. Then you turn this into a data set consisting of tuples of X and Y. So X is your input, that's the design of the protein, and Y is its efficacy for whatever quantity you're measuring. And then you train your predictive model, just like in that paper from NYU and Facebook that I had before. You train a mapping that maps from the input, from the design, to the quantity of interest. And then you can use this mapping to find the best design. This is an inversion process, right? You're mapping maps from design to efficacy, and you're going to invert that to find the design with the largest efficacy, perhaps by differentiating through that model and solving an optimization problem. And then if you like, you could go and collect some more data based on your results. So maybe you have a candidate design, you're not sure if it's good, you test a few more designs kind of in that neighborhood and repeat this process. Or you could just take a fully data-driven approach and just stop at step 3 and just ship that off as your new design. So that seems very sensible. It seems like a very logical approach to using machine learning to design drugs, molecules, whatever. What's wrong with this? Well, okay, so you've got your input X, that's some representation of your design. It could be a protein, it could be a molecule, and this is not specific to biology. It could be like the geometry of an aircraft wing if you want the aircraft to fly as fast as possible. Your output is how good that design is, its efficacy at the task of interest. And the model that you're going to train to map from X's to Y's is some big high-capacity model like a large neural network. It has to be big because the representation of your design is probably going to be fairly high-dimensional. If you want to represent a protein, you need to represent the sequence of peptides. Each of them takes on 20 values, and you're going to have hundreds or even thousands of those values. So the input is high-dimensional. You need a large model. So you collect your data, each design associated with some value. That data comes from some distribution. Let's call that distribution P data. When you train your model on that distribution, you're doing empirical risk minimization. Empirical risk minimization will get you good generalization error if you don't overfit for other samples from the same distribution, from the distribution P data. When you then go to find the best design, the best drug, the best molecule, you would take the argmax of this function. You would actually optimize your X so that this function outputs the largest value. So then we could ask, when we solve this optimization, are we going to get a design X that is in distribution? Meaning, does our machine learning theory actually provide us with any guarantees that our function would give us the correct answer? And the answer is that it doesn't, because we're not constraining X in any way to stay in distribution. That's a very difficult problem. If we just optimize it naively, what we're really asking for is an adversarial example. We're asking for our optimizer to fool our predictive model into producing the largest number. And we know that no matter how powerful your model is, no matter how large it is, no matter how much data was used to train it, you can always find an adversarial example. This is one of the most significant results in machine learning security over the last few years. If the model is trained with expected risk minimization, adversarial examples can always be found. So an adversarial example is basically a small perturbation to your input that fools the model into outputting something else. So you could take a picture of a panda, add a little bit of noise to it in a very clever pattern, and a state-of-the-art ConvNet will classify it as a given. In the same way, you could train your predictive model to output the expected efficacy of a drug, and then when you optimize the design of the drug with respect to that model, it'll tweak it in some imperceptible way and fool the model into outputting a large value. And this is a really big problem in practice. So models that are good for prediction are not necessarily good for design. And that's the problem that this project really aims to address. So we can, to make this a little more formal, we can formalize this model-based optimization problem as the problem where there exists some true function, let's call it f of x, and we don't know what this true function is, and we want to find the optimum of that function. Now, we don't have access to the function, but we have access to samples. We have access to the results of our experiments, those x's and y's, represented as these green dots. And we'd like to fit some kind of surrogate, f hat theta of x, and then take the optimum of that surrogate instead. And if the optimum of that surrogate corresponds to the optimum of the true function, then we're all good. But because of this distributional shift problem, in practice, that surrogate might extrapolate in some unreasonable ways far from the data, and therefore give us the wrong answer. So the obvious solution that we could imagine for this is to somehow constrain our optimization so that we only consider designs that are in some sense close to our data. So maybe we somehow limit our search to this shaded region here so that we don't go to the places where our model will extrapolate erroneously. That's a very reasonable solution. So we could say, well, machine learning theory tells us that our model should work well on samples from P data. Can we estimate P data, the distribution of inputs seen in our training set, and keep X close to that distribution? Unfortunately, in very high dimensions, This is known to be an extremely hard problem. In fact, there are a number of sort of hardness results that show that doing out-of-distribution detection with density models and high-dimensional inputs is difficult for neural nets for the same reason that the adversarial examples are difficult. Basically, if you can fool your predictive model, you can also fool your density estimator. You can sort of fool your constraint into thinking that an out-of-distribution input is in fact in distribution. So you might still be vulnerable to adversarial inputs on your constraint. And there's some very nice work on this. For example, there's a paper provocatively titled, "Do Deep Generative Models Know What They Don't Know?" The punchline is no. And there's this wonderful quote in the paper: "We find that the density learned by flow-based models, VAEs, pixel CNNs, these are all sorts of different density models, can't distinguish images of common objects such as dogs, trucks, and horses from house numbers, assigning a higher likelihood to the latter when the model is trained on the former." And yeah, house numbers look pretty different to humans from dogs, trucks, and horses, so that's a pretty big problem. Okay. That said, there is some work that does do this with considerable effectiveness, including from my colleague Jennifer Listgarten. So actually, a lot of the results that I'll discuss actually directly build on that work and compare to it. So if you want to check that out, check out this wonderful paper by her student David Brooks called "Conditioning by Adaptive Sampling for Robust Design." Okay, but what can we do if we don't want to do density estimation on high-dimensional inputs and we don't want to be vulnerable to these adversarial examples? Well, here's one way we can think about this. So this kind of problem, doing the argmax with respect to x subject to the constraint that we stay within the data, this is hard. And it's hard because x is very high-dimensional. And there are values of x that are basically invalid, values of x that don't correspond to reasonable designs for which we'll get unreasonable predictions, like this adversarial example. However, the output y is one-dimensional. The output y, that's the efficacy, that's the score of your design. So valid values of y are a lot easier to find because it's one-dimensional. You know, you can discretize it, grid it up, and exhaustively evaluate the whole thing. So what if instead of learning a function from x to y, we instead learn a function from y to x? Basically a function that predicts, given a particular level of efficacy, what kind of design would achieve that efficacy. Now, at first this seems like a much harder problem because instead of having a model that just predicts how good a design is, you have a model that actually outputs a design given a level of efficacy. But the input to this function is one-dimensional, so it's a lot easier to do out-of-distribution detection on it. So then you would choose your design to be just the output of this f inverse y for the largest y that is close to the data. And this is a much easier problem because y is one-dimensional, so you just kind of take the largest y in the data set and then increase it by a little amount, and that's your y. So at first this seems like a harder modeling problem, but it's actually an easier out-of-distribution mitigation problem. And that makes it really good for us. It's still not entirely trivial to choose that y, but it's a lot easier. So here's what we're going to do. First, unfortunately, the function f inverse y, the function that maps efficacy to design, is one to many. So there might be multiple different designs that all achieve the same score. So we can't just train f inverse y naively. What we're going to do is we're going to train actually a function f inverse that is a function of y and some other input z, which is kind of random noise. So the idea is that for different values of z, you should output different designs on the level set that all have the score y. So you have a neural network model we're going to train. It's a function of y and z, and it produces designs x. So y is just a real number, it's just our desired score, and z is random noise. And for different values of random noise, this model should produce different designs, but that all have the score y. How can we train a model of this sort? Well, this is precisely the design for a generative adversarial network. So the generator in a GAN is a model that takes in noise and outputs a sample. And the difference is that for us, it's also conditional on y, which is something called the conditional GAN. So a GAN is a model where the generator is trained so that its outputs are indistinguishable from real data according to a discriminator. And GANs have been very successful for all sorts of generative modeling problems, from modeling pictures like people's faces, all the way to actually generating novel protein designs. So this is a paper from Professor Wong's lab at Stanford that used GANs to generate novel proteins, random proteins, not for any particular goal. Okay, so these kinds of models have been used for the types of problems that we're interested in, so that's good, but not for the optimization yet. So that's what this work is about. All right, so then if we can train this GAN model, this conditional GAN, the one question we're left with is which Y do we choose? And the intuition is that we have to choose the Y that's close to the data, but actually we want the largest Y we can get away with. So this choice does become kind of delicate. A simple choice would be to choose the best Y in the data set and slightly increase it. But if we want to squeeze the most performance out of this, we can actually do something a little more subtle, which is we can choose a value of Y so that both the inverse model F inverse and the forward model F actually agree with each other. So we can train both an inverse and a forward model, and we can choose Y as well as the noise Z to maximize the score predicted by the forward model when evaluated on a design outputted by the inverse model. Because the inverse model will only output in distribution designs, so we would expect this to work. Subject to the constraint that the output of the forward model agrees with the thing we initially fed in. So basically F applied to F inverse applied to Y should be close to Y. All right, so putting it all together, we take our data set consisting of designs and scores, and we train two models. We train a conditional GAN to basically learn this inverse mapping from scores to designs, and we train a conventional feed-forward predictive model to map designs to scores. Then we solve this constraint optimization problem to find the best score and extract the corresponding design. And if we like, we could do some more iterative experiments and so on. But this is kind of the basic structure of the algorithm. Experimental results, we tested this on a variety of kind of toy task, image generation. This is kind of a fun task, generate a face with the youngest age. So all the faces in the data set on the left had an age of 15 years or older. The generated faces were then scored by human raters. And these are some of the generated faces. So the top shows real faces that are younger than the best in the data set, just to give you some idea. And then the generated faces were scored by human raters as being, around 12 to 13 years old, so younger than the youngest in the data set. But these are kind of toy evaluations meant to just stress test the method. We also tested on a green fluorescent protein fluorescence optimization problem, which was also used in prior work from Jennifer Listgarten, and we found that our method does, quite a bit better. Here, larger numbers are better. So this is the Brooks et al. Method. Okay, so something here is actually working. That's good. And we're continuing to build on this method and apply it to more realistic settings. We also have some ongoing work developing new model-based optimization methods. I think I'm running a little over time, so I'll skip this, but it's in the slides. One thing I do want to mention very briefly is another thing we're working on is we're designing benchmark suites for evaluating these kind of model-based optimization or data-driven design algorithms. So we have a benchmark that'll be coming out soon called Design Bench, which incorporates tasks centered around a variety of topics from protein design to drug discovery to other science applications like designing better superconductors, designing robot morphologies, designing controllers, and so on. So there's a variety of tasks in this benchmark suite. And we've been testing a range of different model-based optimization methods to benchmark them and to provide this as a kind of a standard for the community to use. All right, thank you very much for listening. I'd like to especially thank my students who were involved in this work, particularly Avaral Kumar, who was the first author on the work that I presented, and I'll be happy to take questions.
Thank you, Sergey.